Log on, tune in, find out. Another good idea from Cambridge.
From British Columbia, who will be speaking about adaptive and stochastic algorithm for piecewise constant EIT and DC resistivity problems with many measurements.
Thank you very much. It's very nice to be here. I'd like to thank the organizers for having me. Can I be heard? Oh, okay. Hi. Okay. So this is joint work with Kees van den Doel, did most of the work. The EIT problem is, of course, a well-known problem in our community. I went to the Wikipedia entry for EIT to see what they have to say about it. And of course, I highlighted what is important for our talk. And so there's the description. You don't have to really read it all. But the point is that you have a bunch of electrodes, for example, in this picture like this, also from the Wikipedia web page. And so this is from a lab, I think, near Oxford. There's a bunch of electrodes, a belt of electrodes, and different experiments are being produced by using different combinations for sources and receivers. Here's the same person connected to electricity, and this is a resulting imaging of the lungs. Okay. Continuing the Wikipedia description, there's been a lot of theory, and in fact, we heard quite at the end of it, in fact, from Kari Stana yesterday. And also, there's a similar problem called DC resistivity. This is what this is, which has been known to the geophysicists since the 1930s, where the mathematical model is rather similar. So let me introduce the notation that I will use for the inverse problem. And the particular EIT or DC resistivity problems are inverse problems that will be included in this sort of framework. So the goal of the inverse problem is to, of the type we're looking at, is to recover a distributed parameter function m of x, which would be the conductivity. And we have two things. We have the forward operator f of m for any given candidate function m. F would be the predicted data. And then there is measured data or observed data, and now we want to find m such that the predicted data agrees with the observed data up to noise epsilon. So if we immediately move to discretization and think of these functions as mesh functions, and then we order them as vectors, then you can think of both m and f as vectors, and then the corresponding Frechet derivative would be a matrix, a sensitivity matrix that we will call J, and we relate to it as matrix because that's what we are going to see in a moment. So we have a sensitivity matrix, and now the particular forward operator that we are looking at is f of m would be as follows. So there's an elliptic PDE. Again, I'm going through this fast because I think everybody has seen it before. It's just my notation for it. An elliptic PDE that is now discretized, and it reads AU equal Q, where U is a potential field, and Q basically says, big Q, says where it is that the data are on the domain. And so f of m, the predicted data would be Q times U. So Q would be the corresponding projection matrix of the field U that solves the PDE. Now we were talking about different experiments, many experiments. Oops. So a multi-experiment of the same version of the same thing here would be where you have the ith source Q. Correspondingly, there's going to be the ith potential field U, okay, and then there is an ith projection matrix Q that says where the data are in the ith experiment, And that gives us the forward operator Fi, and the operator F here is a combination of those Fs. If you have S experiments, F is going to be F1, F2, all the way to Fs, and correspondingly the data will be B1, B2, all the way to Bs. Okay? The point is that A of M does not depend on the experiment. The PDE, as we all know, is the mother of all problems. It was called by Joel Dandy many years ago. Div sigma grad of ui is equal to qi with the Neumann boundary conditions. Okay, so this sigma x, the conductivity, is going to be expressed as pointwise function of m of x, and we will say what m of x is in a moment. Okay, and A of m is a discretization of this PDE. Point is that if we have S experiments, that just in order to evaluate the forward operator, we need to solve SPDs. So suppose we have 1,000 experiments, we have to solve 1,000 PDEs just in order to see what is the result for a particular M. And for anything else, there's going to be many more thousands of this sort. So it.
Are you making measurements on the boundary or inside?
In this case, it will be on the boundary, but the point is that the measurements, even on the boundary, I mean, when you have this belt of electrodes, it's not everywhere. It's a particular combination of sources and receivers that you're looking at. It's going to be on the boundary, but
okay,
you will see. So the point is that you have many PDEs to solve for anything here. Okay, and so if we are not careful, it could be a lot of work, and so we want to be careful. A word about the theory of EIT. There's been a lot of it, as we all know, culminating in the paper by Astala and Paivari. Whoops, I don't know how to pronounce this. Paivarita. Okay. I know that there's a contingency of people here who will pronounce it way better than me.
I pronounce it Taivarinta.
Okay.
I am Taivarinta.
I too. Me too. I will follow you. The point that I would like to draw from this work, in fact, it's a whole long sequence of efforts that try to prove that if the entire Dirichlet to Neumann map is given, then the conductivity sigma of x is uniquely recovered. The idea is to try to make such statements based on weaker and weaker assumptions of continuity on the conductivity sigma. Okay, and the thing that I would like to the conclusions that I would like to draw from this are the following. But of course, in practice, we don't have the entire D2N map. We have noise, we have discretization of the PDEs, and so on and so forth. But still, the theory suggests there are two important things which really we do observe in practice. One of them is that things can go wrong when sigma has discontinuities. Okay, and the other is that many experiments are useful. These are the important things really that one draw from it. On the other hand, so in general, when you have a discontinuous sigma, it's very difficult, in fact, to solve this problem in a meaningful way. However, if sigma is somehow piecewise constant, if you have only a few values of that sigma can take at any x, then this is in fact a much more stabilized problem. In fact, if you think of only two values, namely you have a body and a background. So the background is one value of sigma, and the body is homogeneous as well, and another value of sigma, then the question is only where is the boundary between the body and the background, and so that would be shape optimization. And the assumption that you have just shape optimization is a strongly stabilizing assumption, and in fact this sort of problem can be solved in a much more reasonable fashion in practice than the general one for discontinuous sigma. And so, we finally arrive at the goal of this talk. In less than 15 minutes, we finally arrive at what I would like to talk about. And that is, we want to look at algorithms we are going to use, if you wish, true solutions that are piecewise constant, but we are going to look at algorithms that take or do not take this information into account. And then we want to construct efficient algorithms for the case of many experiments. Okay. So that's the motivation. What I'm going to talk next about is previous work that is related to the newer work that I will mention following that. So this will describe work that has been done until let's say until 2 years ago or so. And then I will describe adaptive algorithms. This will become clear when we get there. So first, we're going to look at two situations. One where we don't know anything about the solution. It is piecewise constant, but we don't know it. And so we're going to, what we're going to do is we are going to look at m of x being log sigma of x, or sigma equal to exponent of m. And that will take care automatically of the requirement, the physical requirement, the sigma be positive. And we discretize this PDE on a staggered grid. This paper did not invent staggered grids by any means, but this is where you can find details of what we did exactly. Okay, this is why I mentioned it. That's one situation. The other situation is where we do assume that we know that there is that is actually a piecewise constant solution, and so in this case we really are looking at a shape optimization problem. The problem then is practically, if you think about it, if you're going to iterate and try to find where is the switch from this value to this value, it's difficult to iterate because as you move, there's an O1 jump as you move. And so what we're going to do is we're going to embed this information in a level set. And that's what's written here, level set function. And this is what's written here. So sigma is going to be the exponent of a projection P of m and of m, where this is defined. Now we are thinking about some discretization of the domain, and the discretization width will be h, and this function basically is going to be what defines the jump, which is spread over one mesh pixel, if you wish. Yeah, so it's like that. So the big thing about the level set function is that whereas the piecewise constant solution is actually only bounded, the level set function is actually differentiable. So you can, it's easier to work with that level set function, and the piecewise constant function, which is what we are after, is defined like so, is defined as the shapes that arise when we basically cut across the level set function with the plane of 0. Is well-known stuff. And just to show you that this in fact works, so this is from papers from 2007. We used, from this paper here, we used the code by these 3 geophysicists. This is the DC resistivity setting with 41 experiments, and this is the true solution. Okay, I mean the idea in all of these is you take the true solution on a finite grid, then we are going to reconstruct. You produce the data, perturb it by noise, and then from that you want to reconstruct the solution and compare it to the true solution, or the ground truth is sometimes called. And this is a result on a 32 cube grid. For those who have ever tried to actually solve this problem, this is a very good approximation to that. And in fact you can get it when you assume a piecewise constant. The piecewise constant, you take the piecewise constant assumption into account in a strong way. Here's another one. This is the true solution. This is the initial guess. This is the result on a 24 cube, if I'm not mistaken, grid. And another one. This is the exact. This is the initial guess, and this is also on a 24 cube grid. So it's possible to actually get something here, which is going to be difficult in more general situations when sigma has discontinuities. So how do we do it? How does anyone do it? Do it? It's a highly imposed problem, and the mother, or maybe I should say the father of all discretizations, of all regularizations is Tikhonov. So what do we do with Tikhonov? We minimize an objective function phi, which is the misfit, the predicted minus the observed data, the norm of that, plus coefficient beta times the regularization operator R of m. Necessary conditions, we see for the first time this sensitivity matrix here coming from the taking a gradient of this term. And then here we have the gradient of the regularization operator R. What is R? We are going to look only at the following R, not TV in this talk. We're going to look only at this R, and the justification for that is that the two scenarios we have is either we don't know anything and therefore L2 is as good as TV. Only when you start knowing something, TV could be better. And on the other hand, if we know that it is piecewise constant, then the Leverset function actually takes care of it. The Leverset function is now differentiable, and therefore it makes sense to actually take a look at the least squares norm of the gradient. Okay? That will be our regularization operator discretized. And so when you plug in this thing here, then this is actually just a very large and somewhat ugly nonlinear least squares problem. So how do we solve nonlinear least squares problems? The flagship method is Gauss-Newton. And Gauss-Newton, basically you iterate, and so in the nth iteration, we have m sub n, and we evaluate everything there, and in fact, the next the correction for the iteration in the nth iteration, delta m, satisfies this system of equations with, this would have been beta. The same beta is here. This is Gauss-Newton. But then we look at it and we say, let's call this beta 0, because this beta talks about the Tikhonov regularization, whereas this term, all it does is it regularizes the iteration, the linear iteration. They have different functions, therefore they should not be the same. So we'll talk about beta 0 and beta in a moment. But before that, the question, let's suppose that we have determined those things. The question is, how are we going to solve this linear system of equations for the correction delta m? And here comes the next problem. The next problem is that J cannot really be evaluated in practice, because J, the sensitivity matrix, involves a PDE solution for every column of a matrix big G that has as many columns as there are mesh points in it. So it could be 100,000 PDE solves just for G, let alone storing it. Better to do for J, for J. It's better to evaluate J transport, but even that is really out of the question. So you want to look only at methods that involve matrix vector multiplications. If you have such as conjugate gradients, if you have that, then it's G times a vector, so that's a vector, so that's just one PDE. If you have one experiment, it's one PDE solved for a matrix vector multiplication involving J, and therefore, for one experiment, we have here two PDE solved, one J times vector, one J transpose times vector, two PDE solves per experiment. So to actually solve this Gauss-Newton, if I have S experiments, then I would have, it would involve 2S PDE solves. So in fact, now finally we can estimate the cost of the operation, and that is exactly what I'm trying to minimize here. So what is the cost? Let's call it W. It can be, the essential thing we do is solve PDEs, and so that would be a unit, if you will, a work unit, if you wish. And so if we have big N outer iteration, Gauss-Newton iterations, in each of those we have big M sub N inner preconditioned conjugate gradient iterations, and some stuff that let's not worry about it. And if we use in the nth Gauss-Newton iteration S sub N experiments, then the total cost would be these 2 times M sub N times S sub N, and we sum that from 1 to big N. Okay? So the cost for each Gauss-Newton iteration is here, and this is the sum over the the outer iteration, the Gauss-Newton iteration. This is the thing that we would like to reduce, because if we are not careful and we just do it, then you can easily get hundreds of thousands of PDEs to solve. So the question is, how do we reduce it? Once again, this is kind of overhead. Let's not worry about that. The essential cost here, there is this m sub n times the number of experiments, okay? And so this is what we would like to concentrate on first. The simplest thing we can think about is instead of iterating with these preconditioned conjugate gradient iterations until the bitter end, maybe just just use a small number of such PCG iterations. Let's not solve delta for, it's only delta m that you're solving for. Let's not do it exactly. And the good news is that this actually has a regularizing effect on the iteration. So in fact, by doing something in order to be cheap, we gain a regularization effect. We actually can take, we actually can take beta 0 to be 0. So we are attempt to solve the singular system directly. And the reason why we succeed is we're not going to go all the way there. We're going to stop after only a few PCG iterations. And this is called iterative regularization, and it is the topic of a book by Hansen that came out of his PhD thesis. It's a great book. The only beef I have with it is that he called this method iterative regularization. I don't know what is not iterative regularization. Everything is iterative regularization, actually. It's a bit too general a name for a particular a method, really. But the point is that what it does, rather than what its name is, and what it does is it basically applies a conjugate gradient least squares iterations to solve this this sort of problem. Okay, GL delta M minus delta B. Delta B is the corresponding data residual. And here's a theorem from Hansen's work. When you apply iterations to this thing, PCG, preconditioned conjugate gradient iterations, then this residual decreases monotonically. So you can actually have some sort of a control. I mean, you can stop this thing when you like the amount of decrease you got. Question is still how to stop it. What should be the criteria? What should be the criterion? Because this is the linear iteration. It's just one iteration of the nonlinear problem. So we need to sort of ask how to choose m sub n as well as big N, the number of total number of iterations. Before doing that, let me just mention that we can also take beta to be 0, and then this actually doesn't stabilize Tikhonov, which was what beta 0 equals 0 was about. This actually replaces Tikhonov by something we call dynamical regularization. And the point here is that instead of Tikhonov, it is, instead of Tikhonov, it is that's not me. Instead of Tikhonov, it is the finite number of iterations big N plus the stabilization at the last iteration that replaces the regularization effect of Tikhonov. And the advantage of the Tikhonov is you don't have to determine this beta. The determination of beta in Tikhonov method is just an annoying trial and error sort of process, and here you avoid it. But there is also a disadvantage. The convergence process is less controlled, and there's less theory to support it. Okay. So this was, as far as this talk is concerned, all I've said until now was background. And now we come to the newer part. And here are two adaptive algorithms. One is to select the number of m sub n, to basically determine m sub n, the number of inner PCG iterations, and then to a stochastic algorithm to select which experiments to use at each iteration. So first, Let's try to determine this m sub n. Okay, so what we can do, I mean, you can say what's the problem actually. I mean, we iterate, right? I mean, so we iterate, and each time we use this conjugate gradient iteration, we stop, we evaluate phi, and then we see if we have enough decrease. Okay. I should say before that the principle we use is that we want big N to be small. It's like an SQP idea. In each iteration, you want to do the best you can, rather as opposed to something like gradient descent, which is cheap and many iterations. So here we want to have not too many iterations. Okay, and so why not simply evaluate phi, the objective function, evaluate it after each PCG step, and when you got enough decrease, stop. The answer is that each evaluation of phi could cost 1,000 PD solves. Okay, so we don't want to do that if we can. And in fact, it turns out that often there is a value for m sub n, a fixed value for m sub n, which is pretty good. The problem is we don't know what it is, and it changes from one application to the next. Okay, so what we do instead is we guess it. We guess m sub n, we sort of jump in, we don't evaluate phi until we get there and one before there. And then basically when we have enough decrease, if we have enough decrease, we are happy. If we don't have enough decrease, we decrease m sub n until we have it. The details are in the paper that is on my website, on my web page. The important point is the idea. The idea is we only evaluate phi for big m sub n and not for everybody else. Okay, and that this is supposed to be sufficient here. And then we determine m sub n by sufficient decrease defined by some magic constants. Again, they are specified in the paper, but actually discussing such details here, I think, is not very useful. So let me show you how it works. So this is a DC resistivity problem on the unit square. We basically have poles here and here on the right and left walls, if you wish, and the sources are of the dipole form. One from the left, one from the right, and if we have let's say 3 here and 3 here, then all combinations of 3 and 3 give us 9 experiments, and we are going to look at a ground truth or the true solution, quote unquote, to be piecewise constant with these sort of values, not values, but rather areas or 3 bodies in the background. And here is an experiment with 9 experiments. Here's an example with 9 experiments. 2.5% noise was added to the data. And this is on a 65 square grid. And this uses Tikhonov with the L2 regularization, meaning L2 on the gradient of directly on log sigma, the gradient of that. And by trial and error, we found that beta for Tikhonov is this value. And what you can see in this table here is what happens when I fix m sub n to be 20. So 20 PCG iterations in each outer iteration. That converges in 4 outer iterations. If I use only 3 in each outer iteration, then I need 26. So it turns out that 26 times 3 is about the same as 20 times 4. So I get here that in both cases I need about 1,400 PDE solves, whereas with the adaptive algorithm you get 1/3 of it. So in fact it's actually very easy to improve on a straightforward algorithm. The reconstruction quality is so poor that I'm not going to show it. The point is that I get it fast. To improve the reconstruction, actually I'm going to need more experiments, but we're going to see that in a moment. Let's look at another example, same as before, but now we do know that it is a piecewise constant. We take this into account by using the level set function representation. Once again, Tikhonov, but as I said, these things do change. So here actually with this level set function, beta equal 10 to the minus 3 was determined to be particularly good, okay, by trial and error. And we here also use the dynamical regularization, denoted D, with different initial guesses. Okay? And so before 20 PCG iterations at each outer iteration was very good. Now suddenly it diverges. In this case, you're trying to solve a singular system too well. Okay, so it doesn't work at all. Whereas 5 is a good number, but the adaptive algorithm is better even than 5. The point is that the adaptive algorithm finds the right thing without trial and error. This is the main thing. And here are results of the reconstructions. This is one initial guess, and this is another initial guess, and the third initial guess is 0 everywhere. Tikhonov gives the same thing more or less for all initial guesses, and that is the reconstruction for Tikhonov. Whereas the dynamical regularization from the 3 guesses gives 3 different reconstructions. One of them, the one starting from m equals 0, is the closest to Tikhonov. And you can see that this is actually quite distant. Both of those are quite distant. It is possible to threshold these values, and then you see black and white more clearly. But in fact, if you just keep it smeared on the mesh width, maybe that sort of suggests that we don't know exactly what it is, which is really the truth. So maybe it's actually a little more of a realistic picture to have these gray value here. There's gray values here. But this is a decent reconstruction for this problem on an exponential ill-posed problem with only 9 experiments. We are very far from knowing the Dirichlet-Neumann map here. Here's another example. It was 2.5% noise, and we just decreased the noise level to 0.8. To see anything, we have to take a finer grid. It's 257 squared. Still 9 experiments. And once again, so just a moment ago, 5 PCG iterations at each outer iteration was the best. Now it is a disaster. Once again, so each time you change something in this problem, the best becomes not so good anymore. Here, 10 PCG per inner iteration, per outer iteration gives the best results, and our adaptive algorithm does better than that. Okay. Time and again, the adaptive algorithm does somewhat better than the best fixed number, somewhat better, but the point is it does it automatically. You don't have to try all kinds of m sub n's. Okay, that's the great thing. It turns out that the reconstruction quality does not improve even though the noise level goes down. And the reason is that 9 experiments is just not enough. We have to take a larger number of experiments. When we have to take a larger number of experiments, the question of cost of the whole thing comes once again to the fore. And so we wonder about using only fewer than S experiments. Can we use fewer than S experiments? Okay. So first of all, I want to remove the possibility that I have that S is huge. Okay, so we started with S very small, but now I want to cap it from the other side. I don't want S to be huge. If I have 1 million data, which sometimes all companies give you that, and it turned out that if I took every 1,000th of them, you know, and use only those, throw away all the rest, and that would have worked, let's say, then I would call this embarrassing redundancy. It's not that I'm embarrassed to have it, it's because the point is that the algorithm of throwing them away is not very sophisticated. It's like embarrassing parallelism, for those of you who know what that is. It's also something that you love to have, but it's the algorithm that comes out of it is simple. So let's assume that actually my S, the number of experiments, really is more or less needed for a good reconstruction. Still, do we really need all of them, all experiments at each iteration? Okay. For example, at the beginning, all I want to know is where to go. So maybe I don't need all S experiments for that. Maybe I need all S experiments only when it's the time comes to refine the detail of the reconstruction. Okay, so it's a different purpose. So it does make sense to let S sub n depend on the outer iteration. So how do we handle that? Okay. So here's the objective function. Once again, here, what we had before was the norm of f minus b. Now let's write it per experiment. Okay, so this is the sum on the experiments of the corresponding misfits, the norm of the misfits. And now, if we introduce a stochastic variable w with the probability distribution that satisfies that the expected value of wi times wj is delta ij, 1 when I is j and 0 otherwise, then this sum can be written instead as the expected value of corresponding sum with wi multiplying fi minus bi. Okay, and of course the next step would be to approximate that expected value. And there's been quite a bit of literature on this. It's a hot area actually. What we followed, actually what initiated us, is a paper by Eldad and two friends of his. And they went in the following way. Okay, so if you look, for example, if you want to minimize variance, it turns out that the good selection of those w's is to have values of plus minus 1, randomly chosen plus minus 1s. Okay. And if you do that with s sub n equal 1, then this is called stochastic approximation. It is considered to be a bit of a funky method. It is better to use a few, not just one, but a few realizations, and that is called stochastic averaging approximation. And that works very well if q sub I is equal to q. In other words, if your receivers are in the same location, only the sources change. If that is the case, then you can write the sum of wifi as follows. Yeah, this is the value. This is the value of that sum. And if q super I doesn't depend on I, then I have QA inverse that I can take out of the sum. And then I have QA inverse times just one source. I mean, the source is a weighting of the sources that I have. Okay? And then suddenly, instead of having 1,000 PDEs to solve, I have only one. But if q sub I is does not depend on I, if q sub I does depend on I, big Q sub I, then I cannot do that. And so for that, we have to look at something else, and that's what we do. Okay, so at this point, we depart from this work. And just because in the case of the EIT, when you're looking at different sources and receivers in this belt of electrodes, you cannot assume that Q super I is independent of the experiment. Okay. So now Q super I does depend on the experiment. And moreover, you really want S sub n to depend on n, because again, the beginning iterations are just getting there. Only the final ones need all the experiments. So we do two things here. First of all, we are going to select RW, which still has to be to satisfy the condition on the probability distribution. What we're going to do is we're going to choose it as columns. We're going to choose randomly columns from the identity matrix, okay, and scale them appropriately. So that means that each choice like that is a choice of one experiment. So we're going to draw a sample of experiments, basically. And using that sample of experiments, we're going to perform our Gauss-Newton step, okay? Inside the Gauss-Newton step, we don't make any change. I mean, we actually stick to the same number, to the same experiments. But when we move to the next outer iteration, we once again may change our choice of experiments. So we perform a Gauss-Newton step using a choice of some experiments. And of course, the question is, all right, so we stop because we have this enough decrease, but the question is, what does it mean? Because we have other experiments. And so we basically keep another set of experiments and cross-validate it by making sure that the same objective function estimated by a different set also decreases. Okay. If it decreases, then we feel good about our choice of the experiments. If it doesn't, we increase the set. So if the iteration goes well, then we can have the number of randomly chosen experiments in the next iteration. At the end, we are cautious. In order to claim that we are done, we actually check all experiments to see that we have a discrepancy principle holds. Again, the details are in this paper that is on my website. Let me show you just how well it works. So of course, the first thing we do is we take the first example we had and we try it now with the new stochastic algorithm, and it doesn't do anything at all because all stars are difficult. It just performs similarly, nothing is gained. And the reason is that s equal 9 is just not large enough. This stochastic thing works only when the number of experiments is large. So now, but remember also that we saw that s equal 9 was just not good enough to get a good reconstruction. So let's increase the number of experiments to 36 and then also to 625. And now we see better results. So with 36 experiments, if we pretend we don't know that the solution is piecewise constant, then here there's a factor of 7 in improved performance. And here there's a factor, this is with the level set function, so we do assume that we know that there are only 2 values. And there's also a significant improvement in the efficiency. If the number of experiments is 625, well, now you see a huge difference. So now suddenly this stochastic algorithm really pays off. So it is not a small improvement by a factor of 2 or 3, which is what most numerical analysis is about. This is an improvement by a factor of 50. Okay, so and it's an improvement over a very efficient algorithm. An algorithm which is already very efficient. It's not fair to compare your next BMW to a bicycle. You have to really compare it to another good car. And so here, first of all, we make sure that we compare it to a relatively efficient, to a very efficient algorithm, except that when S is large, you have a lot of work because the number of experiments is large. So you can see here, there's actually a factor of 50 more or less improvement in each of these results when you have a lot of experiments. So of course now the question is, we started with s equal 9 being not enough. Well, maybe this one is already embarrassingly redundant in a sense. So let's see what kind of quality results we get from this. This is the true solution, and here you begin to see something with 36, not much though. With 36 experiments, this is without assuming any knowledge of the true solution. If you assume that it is piecewise constant, starting with the 3 possibilities that I mentioned earlier, you get these 3 reconstructions. This is not bad actually. They're not bad. This is the best maybe. Here, and with the 625 experiments, now you get something even without knowing anything about the solution. Now maybe it's time to switch to total variation, in fact, after we already started to get something going on. And when you assume, once again, the piecewise constant, you get actually decent approximations. I wanted to show you also something in 3D. It won't take long. Again, something close to what I showed you before. 41 experiments in 3 dimensions. This is a comparison to, we chose a good M sub n and fixed it. This is the plain vanilla algorithm, and compared to the loaded version of both our algorithms, the adaptive PCG iterations and the stochastic. And again, S equal 41 is just not enough to see any serious effect. The improvement factor here is 2.5 or something like that. that's not what makes us jumping up and down with joy. Yeah. So it's just a relatively small improvement. But when these are the results, but when we increase the number to 578 experiments, again I will not, I will skip this, just 578 experiments, the improvement factor here is something like 4 or 5, something like that. And here once again there's an improvement factor of about 50. So also in 3D you can get huge improvements in efficiency by using this stochastic algorithm. Sometimes. Some other times, it doesn't really do much. The example here is Case Van den Doel says that it is kind of an artist's conception of a tunnel between the borders of Mexico and the US. And that is our reconstruction, the good reconstruction. This is the less good because there are some artifacts there, but it also suggests that there is this sort of true solution here as well. Conclusions, let's not worry about these. First, the adaptive algorithm for selecting m sub n works very well, consistently better than the best fixed value. And the relative advantage of the stochastic algorithm varies greatly. Sometimes it's modest, sometimes it's really, really impressive, okay? And what we do with this cross-validation approach is we make the gain when we can make it, and we don't fall apart when we can't. That is the point of the cross-validation. Okay. Here's references that are relevant to this. Thank you very much.
Thank you. Questions, please? I actually have a question. You know, especially when you show this picture, when you have two sigmas, and there are several components and relation to the stability, instability. Did you somehow compare this sort of theoretical results by Mandaki when you increase the number of these dots and see how, you know, this J minus 1 behaves? Which definitely.
Sorry, you increase what?
Well, you have this picture and you have two sigmas. They are disconnected. I call them dots. Then you increase the number of dots and see how your instability grows. There are results on that by Nikolai Mandaki, and I think it's useful to compare. Actually, there is a person here also has results of this instability, Lucarondi. Well, he's not here, but he's around. So he also has results of this.
But the point, by more points, you mean a finer grid or something like this?
Well, you just increase the number. You have sigma 1, sigma 2, but the sort of sigma 1 is embedded in sigma 2, but the number of these embedded parts increases, and then your J becomes more and more your condition settings. Like that. I think it's very much related to what.
I think that what I actually have observed is that if you have not just 2 values for sigma, but maybe 4 or 8.
No, it's just 2 values. It's 2 values, but
I
they
don't know this result.
are different positions. Okay. Look with them. Okay. No questions? Thank you very much, and let's go.